Charged energy is a fundamental concept in physics that describes the ability to do work or transfer heat. Energy can exist in different forms, such as potential, kinetic, thermal, electrical, chemical, nuclear, and others. Energy can also be converted from one form to another, but it cannot be created or destroyed. This is known as the law of conservation of energy. One way to understand energy is to use the equation E=2, which relates energy, E, to mass, m, and the speed of light. Copyright. This equation shows that mass and energy are equivalent, and that a small amount of mass can produce a large amount of energy. For example, nuclear reactions in the sun convert mass into energy, which radiates as heat and light. Another way to understand energy is to use the concept of work, which is the product of force and displacement. Work is done when a force causes an object to move in the direction of the force. For example, lifting a book requires work, because a force is applied to the book to overcome gravity and move it upward. The work done on the book increases its potential energy, which is the energy stored in an object due to its position or configuration. The amount of work done by a force depends on the angle between the force and the displacement. If the force and the displacement are in the same direction, the work is positive. If they are in opposite directions, the work is negative. If they are perpendicular, the work is zero. For example, pushing a box along a horizontal floor requires positive work, because the force and the displacement are in the same direction. Pulling the box back requires negative work, because the force and the displacement are in opposite directions. Lifting the box vertically requires zero work, because the force and the displacement are perpendicular. The unit of energy and work is the joule, J, which is equal to 1 Newton meter, Nm. 1 joule is the amount of work done when a force of 1 Newton causes a displacement of 1 meter. Other units of energy include the kilowatt hour, kWh, the British thermal unit, BTU, the calorie, the ultravolt, EV, the erg, and the foot-pound. Nuclear energy is a form of energy that is released from the nucleus, the core of atoms, either by fission or fusion. Fission is the process of splitting a large nucleus into smaller ones, while fusion is the process of combining small nuclei into a larger one. Both processes release a large amount of energy, which can be used to generate electricity. Nuclear fission is the most common way of producing nuclear energy today. It involves using a neutron to split the nucleus of an atom of uranium-235, a rare isotope of uranium that can undergo fission. The split nucleus releases 2 or 3 more neutrons, which can then cause other uranium-235 atoms to split, creating a chain reaction. The energy released from the chain reaction is in that form of heat and radiation. The heat is used to boil water and produce steam, which drives a turbine and a generator to produce electricity. The radiation is contained and shielded by various layers of protection in the nuclear reactor. Nuclear fusion is the process that powers the sun and the stars. It involves forcing 2 nuclei of hydrogen, usually deuterium and tritium, to fuse together and form a nucleus of helium. The fusion reaction releases a huge amount of energy, as well as a neutron. The energy is in the form of electromagnetic radiation and kinetic energy of the helium nucleus and the neutron. The challenge of nuclear fusion is to create the high temperature and pressure conditions needed to overcome the repulsion between the positively charged nuclei and make them fuse. Currently, nuclear fusion is still in the research and development phase, and no commercial fusion reactor has been built yet. Nuclear energy has several advantages and disadvantages. Some of the advantages are: nuclear energy is a low-carbon source of energy, as it does not emit greenhouse gases that contribute to global warming. Nuclear energy is reliable and efficient, as it can provide a steady and constant supply of electricity, unlike some renewable sources that depend on weather conditions. Nuclear energy is abundant and diverse, as it can use different types of fuel and reactors, and can be found in many parts of the world. Some of the disadvantages are: nuclear energy produces radioactive waste, which is hazardous and requires careful management and disposal to prevent environmental and health risks. Nuclear energy poses safety and security risks, as accidents, natural disasters, or malicious attacks can cause radiation leaks, meltdowns, or explosions that can have severe consequences. Nuclear energy is expensive and complex, as it requires high initial costs, advanced technology, skilled workers, and strict regulations to build and operate nuclear power plants. Electrical energy is a form of energy that is produced by the flow of electric charge, usually through a conductor or a circuit. Electrical energy can be converted to other forms of energy, such as heat, light, or mechanical energy, depending on the device or system that uses it. Electrical energy can also be stored in batteries, capacitors, or other devices that can release it when needed. The basic unit of electrical energy is the joule, J, which is equal to the amount of work done when a force of 1 Newton moves an object by 1 meter. Another common unit of electrical energy is the watt-hour, Wh, which is equal to the amount of power, in watts, multiplied by the time, in hours, that the power is used. 1 watt-hour is equal to 3,600 joules. The commercial unit of electrical energy is the kilowatt-hour, kWh, which is equal to 1,000 watt-hours, or 3.6 megajoules. Electrical energy can be calculated by using the formula E equals VIT, where E is the electrical energy, V is the voltage, or potential difference, I is the current, or rate of charge flow, and T is the time. This formula shows that electrical energy is proportional to the voltage, the current, and the time. For example, if a device with a voltage of 12 volts draws a current of 2 amperes for 10 minutes, the electrical energy consumed by the device is E equals 12x 2x 10x 60 equals 14,400 J or 4 Wh. Electrical energy can be generated from various sources, such as fossil fuels, nuclear fission, renewable resources, or other methods. The most common way of generating electrical energy is by using an electric generator, which converts mechanical energy into electrical energy by rotating a coil of wire in a magnetic field. The mechanical energy can come from different sources, such as steam turbines, gas turbines, hydro turbines, wind turbines, or internal combustion engines. The electrical energy produced by the generator can then be transmitted and distributed to consumers through power lines and transformers. Some examples of electrical energy in daily life are lighting. Electrical energy is used to power light bulbs, lamps, LEDs, and other devices that produce light. The electrical energy is converted to light energy and heat energy by the filament or the semiconductor in the device. Heating. Electrical energy is used to power heaters, stoves, ovens, microwaves, and other devices that produce heat. The electrical energy is converted to heat energy by the resistance or the electromagnetic waves in the device. Cooling. Electrical energy is used to power refrigerators, freezers, air conditioners, and other devices that produce cold. The electrical energy is converted to mechanical energy by the compressor, which moves a refrigerant through a cycle of evaporation and condensation, transferring heat from one place to another. Computing. Electrical energy is used to power computers, laptops, smartphones, tablets, and other devices that process information. The electrical energy is converted to digital signals by the microprocessor, which performs calculations and operations using binary code. Entertainment. Electrical energy is used to power televisions, radios, speakers, music players, video games, and other devices that produce sound or images. The electrical energy is converted to sound waves or electromagnetic waves by the transducer or the display in the device. The origin of the energy of the universe is a profound question that has puzzled scientists and philosophers for centuries. There is no definitive answer, but there are some theories and hypotheses that attempt to explain it. One of the most widely accepted theories is the Big Bang theory, which states that the universe began from a singularity, a point of infinite density and temperature, about 13.8 billion years ago. The singularity exploded and expanded rapidly, creating space, time, matter, and energy. The energy of the universe was initially in the form of radiation, which later cooled down and condensed into matter. The Big Bang theory is supported by various observations, such as the cosmic microwave background radiation, the expansion of the universe, and the abundance of light elements 12. However, the Big Bang theory does not explain what caused the singularity, or where the singularity came from. Some scientists have proposed that the singularity was the result of a previous cycle of the universe, in which the universe collapsed into a singularity and then bounced back into a new expansion. This is known as the cyclic model, or the oscillating model, of the universe. The cyclic model implies that the universe has no beginning or end, but rather goes through infinite cycles of contraction and expansion. 3. Another possibility is that the singularity was not the beginning of the universe, but rather a transition point from a previous state of the universe. This is known as the inflationary model, or the eternal inflation model, of the universe. The inflationary model suggests that the universe underwent a brief period of exponential expansion, called inflation, shortly after the singularity. During inflation, the universe was filled with a mysterious form of energy, called the inflating field, that drove the expansion. The inflating field decayed into different regions of space, each with different physical properties and laws. Our observable universe is one of these regions, which emerged from the singularity and inflated into a large, flat, and homogeneous space. The inflationary model implies that the universe is much larger than we can see, and that there are many other regions, or universes, beyond our horizon. This is known as the multiverse, or the many worlds hypothesis. These are some of the current ideas about the origin of the energy of the universe, but they are not the only ones. There are many other models and scenarios that have been proposed, such as the quantum gravity model, the string theory model, the holographic model, and the anthropic principle. Each of these models has its own strengths and weaknesses, and none of them has been conclusively proven or disproven. The origin of the energy of the universe remains an open and fascinating question that challenges our understanding of physics, cosmology, and philosophy. Energy in quantum mechanics is a fundamental concept that describes the ability to do work or transfer heat at the atomic and subatomic scale. Unlike classical physics, where energy can take any continuous value, quantum mechanics shows that energy is quantized, meaning that it can only take discrete values. This implies that there are certain energy levels that a system can occupy, and that transitions between these levels require the absorption or emission of a specific amount of energy, usually in the form of photons. One of the main tools to study energy in quantum mechanics is the energy operator, also known as the Hamiltonian operator. The energy operator acts on the wave function of a system, which is a mathematical function that encodes the probability of finding the system in a certain state. The energy operator can be used to find the possible energy values in the corresponding wave functions of a system by solving the Schrödinger equation, which is the fundamental equation of motion in quantum mechanics. The Schrödinger equation can be written as h equals E, where h is the energy operator, is the wave function, and E is the energy value. The solutions of this equation are called the eigenvalues and eigenvectors of the energy operator, and they represent the stationary states of the system, where the energy and the wave function do not change with time. The energy operator can have different forms, depending on the system and the potential energy involved. For example, for a free particle, the energy operator is simply the kinetic energy operator, given by h equals 2m22, where is the reduced Planck constant, m is the mass of the particle, and 2 is the Laplacian operator. For a particle in a box, the energy operator is the same as the free particle, but with the additional condition that the wave function must vanish at the boundaries of the box. For a harmonic oscillator, the energy operator is given by h equals 2m2dx2d2 plus 21m2x2, where is the angular frequency of the oscillator, and at x is the displacement from the equilibrium position. For a hydrogen atom, the energy operator is given by h equals 2m2240 re2m. E is the mass of the electron, E is the elementary charge, 0 is the vacuum permittivity, and r is the distance from the nucleus. These are some examples of how the energy operator can be derived from the classical expression of the total energy by using the correspondence principle, which states that quantum mechanics must agree with classical physics in the limit of large quantum numbers. Another important aspect of energy in quantum mechanics is the uncertainty principle, which states that there are limits to how precisely one can measure or predict the value of a physical quantity, given a complete set of initial conditions. The uncertainty principle can be expressed in terms of the standard deviations of two observables, such as position and momentum, or energy and time, as follows: xp2 add 2, where x and p are the uncertainties in position and momentum, and e and t are the uncertainties in energy and time. These inequalities imply that one cannot simultaneously measure or know both the position and momentum, or the energy and time, of a system with arbitrary precision. There is always a trade-off between the accuracy of these measurements and the lower bound as given by the reduced Planck constant. The uncertainty principle reflects the intrinsic randomness and indeterminacy of quantum mechanics, and it has profound implications for the nature of reality and causality. Vacuum energy is the energy that exists in empty space, or the quantum vacuum. It is a consequence of quantum mechanics, which states that all fields, such as the electromagnetic field, have fluctuations even in their lowest energy state. These fluctuations create virtual particles and antiparticles that pop in and out of existence, and generate a tiny amount of energy at every point in space. Vacuum energy is a form of zero-point energy, which is the minimum energy that a system can have. Vacuum energy has several observable effects, such as the Casimir effect, the Lamb shift, and the spontaneous emission of photons by atoms. The Casimir effect is the attraction between two parallel metal plates that are placed very close to each other in a vacuum. The attraction is caused by the difference in the vacuum energy between the space inside and outside the plates, due to the boundary conditions that the plates impose on the quantum fluctuations. The lamp shift is the small correction to the energy levels of the hydrogen atom, due to the interaction of the electron with the vacuum fluctuations of the electromagnetic field. The spontaneous emission of photons by atoms is the process by which an excited atom emits a photon and returns to a lower energy state, without any external stimulus. This is caused by the interaction of the atom with the vacuum fluctuations of the electromagnetic field, which induce transitions between the energy levels. Vacuum energy is also related to the cosmological constant, which is a term that Einstein introduced in his general theory of relativity to describe the energy density of empty space. The cosmological constant can be interpreted as the vacuum energy of the gravitational field, and it affects the expansion of the universe. However, there is a huge discrepancy between the theoretical value of the vacuum energy, calculated from quantum field theory, and the observed value of the cosmological constant, measured from cosmology. The theoretical value is about 120 orders of magnitude larger than the observed value, which is one of the biggest unsolved problems in physics, known as the cosmological constant problem or the vacuum catastrophe. That was all. Goodbye.